would now like to introduce Brian Knight presenting Ingress and Egress filtering for service provider edge ports. Brian heads the engineering team at Nitel. Did I say that right? Okay. Which is a business telecom provider. His team operates a service provider network along with SD-WAN and firewall services. This is Brian's second time presenting at NANOG, and we are certainly happy to have him speaking with us today. Welcome, Brian.
Sounds good. All right. Thank you all for coming and for staying for the final talk of the day. I know that, excuse me. I'm going to be giving a talk about ingress and egress filtering at the internet edge for service provider networks today. I've only got 30 minutes, so let's get right to it. Who am I? My name's Brian Knight. I'm engineering director over at Nitel, AS53828, based out of Chicago. I've been slinging packets for 25 years. We do, at 53828, we do business eyeballs, internet DIA, MPLS, VPNs, layer 2 Ethernet, and SD-WAN. There's my email and my LinkedIn, so you can check out my profile. So in this talk, I want to discuss what was our motivation for doing this project? What were the key decisions that we made? I'll dig into a few select packet forwarding scenarios. I'll talk about how we implemented the filtering. I'll talk about what we saw when we implemented the filtering and tested the filtering. And then finally, a short list of recommendations. I'm sorry, Casey, I might butcher your name, I'm sorry. Casey Decchio's DSAV team from Brigham Young University in October of 2020 notified us of DNS spoofing vulnerabilities for the DNS servers that we operate for our customers. And their team was measuring vulnerability to DNS amplification attacks. So when we got this email, we found that, in fact, DNS spoofing was possible mainly because we had no anti-spoofing enabled on our network edge ports. We did a quick Google search, of course, and we could not find an easy how-to for how to configure that anti-spoofing on a service provider network. So I did what I often do is I posted to NANOG and posed the question to the community. And we found that many eyeball networks in the NANOG community did in fact do ingress filtering. They would also do, they performed egress filtering. They would also block invalid IPs, so they would do ball gun filtering. They would block invalid ports as well, so ports such as NetBIOS, Microsoft file sharing, Sun RPC. And they would also block traffic to critical infrastructure, such as router loopback IPs and internal point-to-point subnets. But even with this guidance, we still struggled to find a clear how-to and template on how to implement this. And that's what this presentation strives to be. It strives to be a template for this. So one of the first resources that the community recommended was BCP 84. The title of that BCP is Ingress Filtering for Multi-Home Networks. Perfect for what we were looking for. It outlines 5 techniques for anti-spoofing measures. Those 5 techniques really boil down to a static access control list placed on edge interfaces versus unicast reverse path forwarding checks. BCP 84 has the same overarching goal as BCP 38. BCP 38 has been widely socialized within the community, but BCP 38 mainly deals with filtering traffic from single home sites into the service provider network. So these are service provider customers sending traffic back in. BCP 84's audience, however, includes any multi-home network. So it's perfect for a service provider network because they're typically widely multi-homed. BCP 84 deals mainly with security at the data plane, so please don't throw out your route maps and your prefix lists. You still need those at the control plane. Not that anybody here would. but please don't throw those out. So going into some of the decisions that we made, as we looked at BCP 84, static ACLs really seem to be the only way. We looked at, I mentioned a moment ago that it has 5 anti-spoofing techniques. So I'll run through those real quick. It talks about loose reverse path forwarding. Loose RPF says that if a route exists within the routing table except the packet, regardless of what interface it comes on. That we felt had too little granularity. We wanted to make sure that if a packet is accepted, we wanted to make sure that there was a valid route going back to it, not just an existing route. So we rejected that. There's a degenerate case where loose RPF will ignore the default route. Again, that isn't going to work for our case. Strict RPF, on the other hand, takes us in the other direction and says, if the route exists in the rib and the packet came from the best destination interface, then accept the packet. That would be fine, except for when the route or when the packet arrives on an interface and it happens not to be the best path at that moment, there's a risk then that the packet would be dropped. So that was too strict. Feasible RPF is the 5th technique that's discussed. If the route exists in the rib and the packet comes in on any valid destination interface, then accept the packet. So in other words, if my BGP route for a prefix is received on multiple interfaces, even though my router is only going to install one path in the forwarding information base, the FIB, inbound traffic would still be permitted on both paths. That seems perfect for our application, except for it didn't seem to be an option on iOS XR. So we decided on static ACLs. In terms of what to drop, we decided that we were going to follow as many of the NANOG recommendations as we could. We wanted to block invalid traffic on egress as well as ingress. We wanted to block bug-on traffic in and out. We wanted to block multicast traffic as well. Any invalid services or ports should also be blocked. And initially, we focused on UDP and TCP port 0 and port 445. And then finally, infrastructure. We said that except for ICMP and traceroute, nothing should be permitted to hit our router loopbacks or internal point-to-point links from outside our network. So for us, being a smaller ISP, ease of administration was key. We said that the implementation should be the same on every device. So what that meant for us was we wanted to implement the same set of ACLs configured the exact same way on all of our edge routers. And we wanted to, not only that, we wanted to use the same object groups even, and have the object groups have exactly the same prefixes on every router. That way, we could deploy a change and have it consistently deployed across the entire fleet. So I don't have time to go through every packet forwarding scenario, and I'm not going to, I simply don't have the time for it, but I do want to call out a couple of key ones. So in this scenario, we have a packet coming in from one of our upstreams, sent from someone out on the internet, and the source IP is one of the networks that we ourselves originate in this example. So the service provider network originates 192.0.2.0/24. Packet has 192.0.2.1. We want to make sure that that would be blocked on ingress. However, for customers where we would disaggregate some of our own space and assign it to them to announce to another provider, and you'll see in the corner where I have AS6449 originated networks. assuming for the moment that you could announce a /29 to the larger internet and not be blocked by a prefix list. What I have here is a packet originating from 203.0.1.113.100, which falls within the originated networks that were assigned to 64499. And that packet is traversing their other provider, coming through one of the service provider networks upstreams, coming back into the SP network. And we want to permit this because if that link to the service provider network, we still want to be able to offer services to that customer, even though their connection to us may be down. So we made a choice to permit that traffic. Just one other scenario. On egress, we have the customer, again, running BGP. They're originating some traffic that isn't part of their network set. So they would send a packet with some bogus address. Normally, our prefix lists to that customer should catch that traffic and block it. But in case it doesn't, in case of misconfiguration, we now have another layer of protection against that customer being able to send that traffic outside of our own AS. So in terms of implementation, this is exactly what we did. We implemented what we decided, which was we wanted the static ACL approach. We configured the 4 ACLs, inbound and outbound, for V4 and V6. Made sure to configure the object groups. And we achieved the goal of making the content the same across all of the routers. So I wanted to walk through some of the object groups that we set up. The first 3 groups, the IX group, peer WAN, and tran WAN, those all contain the directly connected subnets. So for the IX, for example, it would be the /24 or /23 put into that object group and then referenced in the ACL. For peer and tran WAN, as you can see, it's the /30s or /126s. For the IPv4 cust, those were our customer provider independent and provider assigned prefixes. So anything that a BGP customer might use and might send out on our across their backup WAN connection, we want to make sure that traffic is then permitted inbound. IPv4 and IPv6 bogon, those are the list of invalid prefixes. IPv4 infra, that's all of our router loopbacks and point-to-points that we wanted to specifically protect against outside attacks. And then BGP-AG, those are the prefixes that we would have configured in our network statements in BGP on all of our routers. And then the last group is an interesting one. Backdoor host was created for possibly valid traffic that was observed during implementation. I'll get into that in just a little bit with in the observation section. And there are 4 static ACLs, PV4 INET in, INET out, and then V6 in, V6 out. In broad strokes, this is what the ACL looks like. This is the intent of the ACL. The very first part of it is we're going to block the invalid prefixes, the address space that should never be used on the internet. Next, we're going to block the invalid ports. Then we're going to permit all of the traffic to and from those transit IX and peering directly connected networks. Then we deny multicast. Next, we permit where the source is BGP customer IP space. So this is where that path from the customer's backup connection or primary connection can come back into our network to be able to use services. Next, we deny where source equals aggregate IP space. So that's our anti-spoofing rule. And then next, we permit any traffic where the destination is our aggregate or our customer's IP space, and then deny any at the end. On the egress side, looks very similar. We start out same way, denying bog-on IPs, denying invalid ports. We permit all traffic on the directly connected networks, deny multicast. We then permit where destination equals customer IP space. It may seem a little bit odd, but and it is. What this does is it covers a strange behavior that we uncovered during testing, and I'll get into that when we get into the observation section. Next, we permit where the source is a NITEL aggregate and customer IP space that lets valid traffic out, and then deny any at the end. So our plan was to create the initial ACLs and apply them to our ports. We enabled blocking for bog-on ports bog-on prefixes immediately, but where rules were intended to be deny, we made them permit and log entries for the testing period, so that we didn't accidentally block anything that was bona fide traffic. And then our plan was to analyze the logs for the matching traffic, and we would then go through a cycle of refining that ACL until finally unwanted traffic only unwanted traffic was being logged, and then we would switch that permit to deny. So during our traffic review, we took the logs, we processed them into a big CSV file, dumped it into Excel, created a pivot table to summarize and view the data, cross-reference that with our systems. And what we saw was that for bog-on prefixes, there were no surprises there. Everything that we saw that was logged appeared to be traffic that was unwanted. On the invalid port side, we saw that port 0, initially we saw a lot of random traffic. And we, as we dug into it, we found that IOSXR actually logs fragments with port 0 because the router doesn't have necessarily the full layer 4 information. So it defaults to port 0. So we saw this long list of ports, and we're like, what in the world was this? We came to find out that it was actually ICMP fragments. So we added a specific rule to block those ICMP fragments silently, and that noise went way down. Once that noise went down, we saw plenty of scanning and abuse. No real traffic was observed. And many network tools just don't even permit the use of port 0. But we did see that traffic. For port 445, we did observe traffic that appeared to be bona fide. We found a customer using it between several of their sites. And they had been sending that traffic out of our own network to internet destinations. It did appear to be bona fide. We decided to abandon it in case that traffic truly was legitimate. So we, in the current state, the invalid port ACL only blocks port 0. The infrastructure side, a lot of abuse hit our infrastructure. It was all different ports. None of it was valid traffic, except for that IPsec tunnel terminating to an old concentrator. Fortunately, we found that the hard way. But fortunately, we were able to find that and rectify that problem very quickly. So as we analyzed the traffic, we found many what I call MPLS VPN IPs coming back in via our transits. These are IPs that we assign to our MPLS customers. So they're globally unique, but they should never be routed across the public internet. Yet we were seeing that traffic come back into our AS. So our theory was that these customers likely didn't have firewalls, or likely had firewalls. I hope they have firewalls. That they didn't NAT for the globally unique IPs. So all of that traffic, there were TCP sessions that were trying to be set up. They obviously weren't completing, so we didn't do anything special for those. We chose to block those. On the inbound anti-spoofing side, I mentioned earlier the backdoor routing, or the backdoor object group, and this is where it comes into play. We did find a few internet WAN IPs with that backdoor routing, where they were coming back into our AS from outside, and those, interestingly enough, seem to be working. So, in the interest of not breaking things, those were explicitly permitted. They have the object group that I talked about earlier, and they have an entry in the ACL. On the catch-all deny rule, we didn't see any significant traffic. On the outbound side, we saw where we were trying to send a lot of traffic from other carriers' MPLS VRFs where the WAN IP wasn't assigned to us. So one thing that used to be very common on our network was we would buy a handful of VRFs or a handful of circuits from another provider, and then we would take their MPLS network and then connect it to our global internet VRF. Well, a lot of these other carriers would assign their own WAN IPs. So in some cases, we had routers that were trying to connect outbound to the internet using that WAN IP that the other carrier had assigned. Now, of course, it couldn't communicate. We also saw lots of other backdoor connections where the customer router would receive traffic on another provider's WAN IP, and then the reply would be sent through us. And both of these types of traffics, or both of these types of situations, we didn't see any valid traffic, so those were blocked. So this is a really, this was the most interesting case to me as I was digging into this. We had a situation where BGP customers would send traffic from their AS. They would use the other provider to send the traffic up to a content provider. But that reply from the content provider would come back to us through some routing policy. I hadn't worked out exactly how this could have happened, but the reply traffic would be routed across the IX to us, and then we would route that traffic right back out to one of our transit providers to go back to the customer. So as you're implementing this, if you implement this on your network, you can't assume that BGP customer traffic will be routed to them directly through you. It might touch your network before it's routed back out of your network and then comes to them through that alternate path. On the administrative side, the new ACL, of course, carried process and procedure implications. Any new BGP customer must have their prefixes added to the relevant object groups on all routers. Any new aggregate blocks that you purchase, they need to be added to the aggregate groups. And one thing that was a difficult shift for us was, if a customer calls in with an issue where traffic is not getting through, we might need to look at those filters. It could be that traffic is being dropped at your edge. But fortunately, in practice, this has not cost us that much in terms of admin time. We had 2 issues with this since implementation, and both of them were resolved very quickly. Lastly, after implementation, we checked back with the DSAV team, and they showed we were no longer vulnerable to that spoofed DNS traffic. So, quick set of recommendations. Agree internally what you plan to block. Get all the stakeholders involved early and communicate often, and test, and test some more. Start with the rules that permit, start with the changing the deny rules over to permit and log those. And run down, make sure you just run down everything in your logs before you switch those rules to deny. Shouldn't be any surprises here. A little bit of future work. We're looking at doing some automation of the object group management. We're looking at doing further security analysis and lockdown of the point-to-point subnets. Right now, these are open wide from any subnet to the /30 or /126. A better practice might be to block all unnecessary protocols. So that might be an area of future work. And further characterization of the infrastructure subnets. Deciding what we want to, what specifically we want to block. Is this blocking enough? Should we be doing more? And that's all I have. I do want to stress in the appendix of this slideshow, I do have an example of some of the object groups that we set up. So this is a sample of what we've actually configured on the routers. A sample of the access list. These are actually the access lists that we've deployed. And then at the very end, there's a short list of references. And with that, I'll take your questions.
All right, we do have a few questions on the virtual platform. Avi Friedman asks, was there any concern about volume of ACL deny locking on CPU, and was there any impact seen?
There was a concern. With the way that the ACL is structured, certainly we did have a concern. We did look at the capability of our hardware. We run ASR 9900 routers, and those seem to have more than enough capacity. So it was something that we looked at, and fortunately it hasn't been a problem.
Okay, still no one in person. I've got another question for you here from Matthew Pitek. It says, good talk, Brian. If you blocked all port equals 0 traffic, does that imply you blocked inbound fragments that could legitimately be destined for your customers? Did that generate many customer complaints?
It did block fragments, and that has not generated any customer complaints to date.
Awesome. And one more from virtual. Tony Tauber asks, I'm not positive that I followed it all correctly, but if the same broad inbound ACL forcing source within your address space, does that mean a customer could spoof another address within that same space, e.g. assigned to another customer?
Yes, there is that risk.
Okay.
Yes, absolutely. We regarded that risk as low to medium. A real goal was to block the majority of the noise. You're absolutely correct, and that could be an area for future work.
Yep. Anybody else have any questions here? Well, thank you for your time, Brian.
All right. Thank you so much.
Put this down and grab the notes again.